All right, welcome back everybody. In this video, we'll be just working through a few additional section 6.2 examples. So in our first example, the story goes, a survey indicates that for each trip to the supermarket, a shopper spends an average of 45 minutes with a standard deviation of 12 minutes. We want to find the probability that the typical shopper will be in the store for between 24 and 54 minutes. So what we'll want to do is start by making a sketch, as always. So we'll draw a picture of our normal distribution. And then we should draw the mean on there at the middle, of course. That will be at 45 minutes. And we're interested in the probability that a shopper will be there between 24 and 54 minutes. So basically this proportion of the whole set of data. So as always, we're going to need to turn our given values, the 24 and 54, into standard normal values so that we'll be able to use our z-table and calculate probabilities. So our mean is going to be 0, and then let's get some z's. So for 54 minutes, z is x minus mu over sigma. Our x here is 54, our mu is 45, and then our sigma was 12 minutes. So let's go ahead and calculate that. That works out to be about 0.75. For 24, z is x minus mu over sigma. That will be 24 minus 45 over 12. And then let's calculate that. That's negative 1.75. Okay, so negative 1.75 corresponds to 24 minutes, and 0.75 corresponds to 54 minutes. So then we need to find the amount of area between those two cutoffs. So using our z-table, the probability that z will be less than 0.75. Looking at our table, 0.75 will give us an area of 0.7734. All right, and then for the other part, we're going to use our new negative z-score table. We want for probability for z being less than negative 1.75. So looking at our negative z-table, negative 1.75, I didn't copy over enough rows. So sorry about that. 1.75, 0.0401. Let me go and get that row and add that onto the video. I'll do that. So the difference between the two is what we want. The area to the left of 0.54 is 0.7734. The area to the left of negative 1.75 is at 0.0401. So the difference is what we want. And that's 0.7333. All right, so let me go ahead and get that piece of the All right, so now just to go back, for the negative 1.75 z value, looking in our negative z table, along the left side, we'll have negative 1.7 for the whole numbers of tenths part, and then 0.05 for the hundredths place. So reading down our probability here at the bottom, 0.0401. All right, so another example. For women in the US, aged 40 to 49, the total cholesterol has a mean of 183 milligrams per deciliter with a standard deviation of 37.2 milligrams per deciliter. We'd like to know what percentage of these women have a total cholesterol that is less than 200 milligrams per deciliter. So as always, a good idea is to start with a sketch. So we'll draw our normal distribution. We'll locate the mean in the middle. That's 183. We're interested in being less than 200. So that will be everything to the left of that point. So we're going to have to convert our x values into z's. The mean of the distribution is at 0. For the standard normal distribution, for the x's, it's at 183. So we'll use our z-score formula to get the z that corresponds to 200 milligrams per deciliter. So our x is 200, our mu was 183, and then our sigma 37.2. So then let's compute. Works out to 0.4569. We'll round that to 0.46. For z values, you can always convert those or round those to just 2 decimal places, because that's all that there is in the z table anyways, is the hundredths place. So then the probability that z will be less than 0.46 using our positive table is 0.6772. So it'll be 67.72% of women will have a cholesterol under 200 milligrams per deciliter. Okay, this next example has to do with IQ scores. For particular IQ tests, scores have a mean of 100 with a standard deviation of 15. We want to know what IQ scores would be in the most extreme 5%, either on the low side or the high side. So again, the mean is 100. We want to know what scores would make up the highest and lowest 5%. So this is a little different in that we don't know the x values actually, but we do know the percentages or proportions. So we just need to work backwards. So looking in our picture, if we have the highest and lowest 5%, those two together make up 10%. And under the whole curve is 100%. So in the middle here, the unshaded part has to be 90. So then, using our z table, up to this point, we should have the 0.05 in the left tail and the 0.90 in the middle. So altogether, that's 0.95. Looking at the body of our positive z table for 0.95, we could see that we'll have a z value of 1.645. Using symmetry, the other end is negative 1.645. Before we go any further, make sure that you're understanding where those values are coming from in the table. So now, those were z's. So we'll need to move those down a bit. We'll need to work backwards to find x values. All right, so those are z's, these are x's. So we don't know what the two IQ scores that would correspond to those two z's are. So we're going to solve, use a little algebra. So for 1.645, That will be x minus mu over sigma. So then solving for x, let's see what we get. 124.67, we'll call that 125. I'm rounding to the nearest whole number here because IQ scores are usually reported as whole numbers. So at the higher end, it's 125. We'll do it for the other end as well. For the lower 5%, that works out to be about 75. Okay, so then to summarize that, basically scores below 75 are in the low 5%. And scores above 125 are in the top 5%. All right. Next, we want to know what percentage of IQ scores are above 133. My guess is it's going to be relatively few because 133 is more than 2 standard deviations above the mean, but let's find out. So our x values are 100 for the mean and 133 for the particular x we're looking for. For z's, the mean will be 100, and we need to calculate what the z for 133 is. Z is x minus mu over sigma. That will be 133 minus 100 over 15. And that's 2.2. So then using our table, the probability that a z will be less than 2.2 is 0.9861. That's the area to the left, right? We wanted the right tail, so 1 minus 0.9861 is 0.0139. So about a 1.4% chance of someone having an IQ score above 133. All right, so we want to take a look at our next example. So in this one, it says scores for a civil service exam have a mean of 75 and a standard deviation of 6.5. To be eligible for civil employment, you have to score in the top 5%. What would be the lowest score you can earn on this test and still be eligible for employment? So again, our mean is going to be 75. We need it to be in the top 5%. So we know the probability this time, or the amount of area under the curve. What we don't know is what score would correspond to that top 5%. So we do know that the standard deviation is 6.5, so we can use that to help us find out what the corresponding value is. So if 0.05 is in the right tail, then that means that to the left has to be 0.95. Looking in the body of the table, for our Z, it's 1.645. That is, the probability that Z will be less than 1.645 is 0.95. The probability that Z will be greater than 1.645 is 0.05. All that's left to do is to turn that 1.645 back into an X value. So we have 1.645 X minus mu over sigma. And then we just need to solve that for X. All right, and that looks like about 85.7 for our cutoff score. If someone scores an 85.7 or higher, they will be in the top 5%. Okay, next. This example says the birth weights of babies are related to the gestation period, that is the length of the pregnancy. Suppose that for babies having a gestation period of 37 to 39 weeks, the mean is 7.31 pounds with a standard deviation of 1.11 pounds. We want to find the probability that a baby will be born at 38 weeks, that is in the relevant time period, and weighing more than 9 or less than 6 pounds. So again, a picture is a good place to start. So the mean was 7.31 pounds. We're interested in the probability of being more than 9 pounds or less than 6 pounds. So what we'll need to do is turn those two X values into the corresponding Z scores and look up a couple of probabilities. Let's start with 6 first. So Z is X minus mu over sigma. That's 6 minus 7.31 over 1.11. Remember that anytime you have a value below the mean, it should have a negative Z value. We'll end up with negative 1.18. We'll worry about the areas in a minute. For a Z of 9, Z is X minus mu over sigma. That's 9 minus 7.31 over 1.11. And that's about 1.52. Okay. So now we need to take a look in our tables and get a couple of probabilities. The probability that Z will be less than negative 1.18 using our negative Z table, negative 1.18 has a probability of 0.119. Okay, that takes care of this part. In the left tail, then for the other part, the probability that Z will be less than 1.52, working towards getting the right tail. For 1.52, it's 0.9357. Remember that that's the area to the left of 9, though. So we actually want the complement. And that's 0.0643. There's about almost a 6.5% chance of being more than 9 pounds and almost a 12% chance of being less than 6 pounds. We wanted to know the probability of one or the other. Since it's an or problem, we're going to be adding together those two probabilities. And so that's about 0.1833. Almost done. We have only about one more example. All right, so here, the monthly utility bills in a certain city are normally distributed with a mean of 100 and a standard deviation of 12. We want to find the probability that a randomly selected bill will be between $80 and $115. So as you know, where we'll start is by drawing a picture. The mean is 100. We want to know the probability of being between $80 and $115. And those are X values. We'll need to figure out the corresponding Z's next. So for 115, Z is X minus mu over sigma. That's 115 minus 100 over 12. And that should be 1 1/3. Or 1 1/4, sorry. And then we need for 80, Z is X minus mu over sigma. That's 80 minus 100 over 12. And that one's negative 1.67. Okay, so now we want the difference between two areas. The probability that Z will be less than 1.25 using our table 1.25, that's 0.8944. And then the probability that Z will be less than negative 1.67 for negative 1.67, that is 0.0475. So then the area that we want is the difference between those two. So that is 0.8469. All right, so that's the last example. I hope taking a look at these examples has been helpful. Make sure to review them and make sure you understand where each of the answers is coming from. And then as always, if you have any questions, let me know.